For decades, physicists have been hunting one of the most elusive targets in science: determining the exact mass of neutrinos. These ghostly particles, so light they were once thought to be massless, continue to surprise us. The latest breakthrough comes from the Katrin experiment in Germany, which has just set the strictest limit yet on neutrino mass. Their new findings show that neutrinos must be lighter than 0.8 electron volts, or about 1.4 10⁻36 kilograms. This represents a significant 30% improvement over previous measurements. To understand why this matters, we need to appreciate just how strange neutrinos are. They're among the most abundant particles in the universe, about 1 billion times more common than atoms. Every second, trillions of neutrinos pass through your body without you noticing. They barely interact with ordinary matter at all. In fact, a neutrino could pass through a light year of lead. That's about 9.5 trillion kilometers, without hitting anything. This makes them incredibly difficult to study. The story of neutrino mass begins with a puzzle from the 1960s. Physicists studying nuclear reactions noticed that some energy seemed to be disappearing. This led Wolfgang Pauli to propose the existence of an invisible particle carrying away the missing energy, what we now call the neutrino. For years, scientists assumed neutrinos were massless, like photons. But in 1998, the Super Kamiokande experiment in Japan made a shocking discovery. Neutrinos can change from one type to another as they travel, a phenomenon called oscillation. This proved they must have some mass, however small. This posed a problem for the standard model of particle physics, our most complete theory of fundamental particles and forces. The original standard model assumed neutrinos were massless. Their having mass means the model is incomplete. Measuring exactly how much mass neutrinos have could point us toward new physics beyond the standard model. That's where experiments like Katrin come in. Katrin, which stands for Karlsruhe Tritium Neutrino Experiment, is located at the Karlsruhe Institute of Technology in Germany. It's essentially the most sensitive scale ever built, designed to weigh the lightest particles in the universe. The experiment works by studying radioactive decay of tritium, a heavy isotope of hydrogen. When tritium decays, it transforms into helium while emitting an electron and a neutrino. By precisely measuring the energy of these electrons, scientists can infer properties of the accompanying neutrinos. Here's why this works. In any radioactive decay, energy must be conserved. The total energy released by the tritium nucleus gets divided between the electron and neutrino. Most electrons carry away nearly all the available energy, leaving very little for the neutrino. But occasionally, an electron gets just slightly less than the maximum possible energy. And that missing bit must have gone to the neutrino. By finding these electrons with energies just below the maximum, Katrin can estimate the neutrino's mass. The challenge is that these telltale electrons are extremely rare. Katrin's tritium source produces about 25 billion decay events per second, but only a tiny fraction of these produce electrons in the precise energy range needed to measure neutrino mass. To detect them, the experiment uses a 200-ton spectrometer that measures electron energies with unprecedented precision, accurate to within about 1 × 10^31 joules. After years of data collection and painstaking analysis, the Katrin team has now determined that the neutrino's mass must be less than 0.8 electron volts. To put this in perspective, an electron, itself an extremely light particle, weighs about 501,000 electron volts. So neutrinos are at least 600,000 times lighter than electrons. If an electron were as heavy as a person, a neutrino would weigh less than a postage stamp. This new limit has important implications. First, It helps cosmologists understand how neutrinos influence the formation of the universe. In the first second after the Big Bang, neutrinos were so energetic that they affected how matter clumped together to form galaxies. Knowing their mass helps explain why the universe looks the way it does today. Second, it constrains theories about what neutrinos actually are. Some physicists speculate that neutrinos might be their own antiparticles, a possibility that could help explain why the universe contains more matter than antimatter. The measurement also impacts the search for dark matter. While neutrinos aren't dark matter candidates themselves, they move too fast. Their properties affect how we look for dark matter particles. More precise neutrino mass measurements help physicists distinguish potential dark matter signals from neutrino backgrounds. Despite this progress, many neutrino mysteries remain. We still don't know the exact masses of the 3 known neutrino types: electron, muon, and tau neutrinos. We only know the differences between their masses from oscillation experiments. Katrin measures something called the effective electron neutrino mass, which combines all 3. Future experiments will need to disentangle these individual masses. Another open question is why neutrinos are so incredibly light compared to other particles. In the standard model, particles get their mass from interacting with the Higgs field, but this mechanism would predict neutrino masses similar to other leptons, like electrons, not the extremely tiny masses we observe. This suggests neutrinos might get their mass through some completely different process, possibly involving undiscovered particles. The Katrin collaboration isn't done yet. With upgrades to their equipment and more data, they hope to eventually reach a sensitivity of about 0.2 electron volts. Other experiments, like Project 8 in the US and Holmes in Italy, are pursuing complementary approaches using different techniques. Together, these efforts may finally pin down the absolute neutrino mass within the next decade. Beyond pure scientific curiosity, why does neutrino mass matter? History shows that investigating tiny discrepancies in physics often leads to major breakthroughs. The slight wobble in Mercury's orbit hinted at general relativity. Small anomalies in radioactive decay led to the discovery of neutrinos themselves. Similarly, understanding why neutrinos have such peculiar masses may reveal entirely new laws of physics. This latest measurement from Katrin represents an important step towards solving one of particle physics' longest-standing puzzles. Each time we push the limits of our ability to measure neutrino mass, we learn more about these mysterious particles that fill our universe, yet barely interact with it. The journey to understand neutrinos continues to challenge and inspire physicists, reminding us that even the smallest things can hold the biggest secrets.